Welcome to the deep dive. Today we're diving into something, well, pretty essential for making sense of things, visualizing data.
It's everywhere, isn't it?
Yeah.
Numbers, stats.
Totally. It can feel like you're drowning in them sometimes, but there's this secret weapon almost, a way to cut through all that noise.
Yeah, to actually see the story behind the numbers.
Exactly. And one of our guiding ideas puts it perfectly. The first thing to do with data is to draw a picture. Always.
That's the core of it.
So that's our mission today, exploring these pictures, these graphs, and seeing what insights, jump out.
Precisely. We're going to unpack some fundamental concepts, and our main source for this exploration comes from materials designed for AP statistics.
Okay, AP stats. Sounds serious, but...
Well, don't let the name scare you.
Yeah.
These are really the foundational ideas, useful for anyone, really, who wants to quickly grasp information and avoid that feeling of being buried by raw data.
Right, building that understanding of how data actually communicates.
Exactly. It's about effective communication.
Okay, let's get visual then. Our source highlights a few key ways to picture data. Each one's got its own, strengths.
We're talking bar charts, dot plots, histograms, and stem plots.
Gotcha. And we'll look at what kind of info they handle best, what angle they give you. So, let's start with bar charts. Those seem pretty familiar.
They are. Bar charts are basically for categories. They really shine when you're visualizing categorical or qualitative variables.
Qualitative. So things that fit into distinct buckets, like different types of cars, maybe.
Perfect example.
Yeah.
Or survey responses. It's different from quantitative variables, which are, actual numerical values you can measure, like height or temperature.
Okay. And in a bar chart, the bar itself, its height.
Right. The length or height of the bar shows you either the frequency, or the proportion or percentage for that specific category.
Makes sense. We've got an example here from January 2015, a survey of 2,000 parents about the school year length.
What'd they find?
Well, 1,100 liked the standard, 180 days. 300 wanted shorter, 160 days. 500 preferred longer, 200 days. And 100 didn't really have an opinion.
Okay, so you can easily picture that bar chart, 4 bars, right?
Yeah.
Labeled with the day counts.
Yeah, and the height of each bar just instantly shows you the preference. You see right away 180 days was the most popular.
And that's the beauty of it, that easy comparison between distinct groups. You see the front runner immediately.
So comparison is key.
Absolutely. And with all these visuals, something our source really stresses is labeling and scaling. Super important.
The details. Like titles and axis labels?
Exactly. You need clear titles, clearly marked units on the axis. Without that, the graph kind of loses its meaning. It can't communicate properly.
And point.
Yeah, they even mentioned, in the AP stats context, you can actually lose points for missing labels.
Huh. Okay, good reminder, even if we're not taking the test. So, moving on. Dot plots. These sound a bit more flexible.
They are, yeah. Quite versatile, actually. You can use dot plots for both categorical and quantitative data.
Oh, okay. How does it work for categories?
Well, you'd have your categories along an axis, like a number line. Then for each person or item in a category, you just put a dot above that category label.
Simple enough.
It is. Simple but powerful for seeing how things stack up.
We have a fun example here. Student votes for favorite dance music artist. Justin Timberlake got 8, Ray Dalton 5, Nate Ruess 6.
Okay, I see.
Charlie XCX 3, Demi Lovato 5, Mickey Echo 3. So the dot plot would just list the artists.
And you'd see stacks of dots above each name. 8 dots for Timberlake, 5 for Dalton, and so on.
Right. You'd spot the popular ones and maybe the ones nobody really voted for pretty fast.
Exactly. Quick visual comparison. And the source also gives an example for quantitative data lengths of stay in a hospital measured in days.
Okay, so how would that look?
Imagine a number line showing the days, 1 day, 2 days, 3 days, etc. Then above each number, you stack dots representing the patients who stayed that long.
Ah, so you'd see if most people stayed 3 days or if there were some really long stays maybe.
Precisely. You see the clusters, the overall range, any unusual values, outliers.
Got it. Okay, now, histograms. These sound a bit more formal, especially with terms like bins.
Right. Histograms are really, really useful when you have large sets of quantitative data, numbers again.
But different from dot plots, how?
Well, instead of plotting every single data point individually, histograms group the data into intervals. These ranges are the bins or classes.
Okay, grouping.
Yeah. And the height of the bar in a histogram tells you the count, the frequency, or the proportion, the relative frequency of data points that fall within that specific bin.
So it's about groups of values, not individual ones.
Exactly. And the source makes a big point about interpretation, being able to look at the shape of the histogram and understand that distribution is really key.
We even get a tech tip. for TI-84 calculator users.
Oh, yeah?
Apparently, you can make them using the STAT menu, STAT PLE, pick the histogram icon, tell it your data list,
Mm-hmm.
and then use zoom stat or tweak the window settings, especially XSCL, which sets the bin width.
That's handy. Practical steps are always good. So let's look at an example. Number of AP classes taken by 2,200 seniors.
Okay.
Results were 400 took 0, 500 took 1, 900 took 2, 300 took 3, and 100 took 4.
So a histogram would show bars for 0, 1, 2, 3, 4 classes.
Right, and the height of each bar would represent those counts, 400, 500, 900, and so on. You'd visually see how students are spread across those AP loads.
And the source points out something important, whether you use the counts or the percentages.
The relative frequencies, yeah.
The actual shape of the histogram stays the same. We even have the relative frequencies calculated here. 0.18 for 0 classes, 0.23 for 1, 0.41 for 2.
That's a really crucial point, because relative frequencies let you compare distributions, even if the total number of people is different.
Ah, okay. So you could compare these 2,200 seniors to, say, a smaller group of 500.
Exactly. By looking at the proportions in each bin, you get a fair comparison, regardless of the overall group size. It levels the playing field.
That makes sense. We have another cool example. A histogram for pairs of shoes owned by 2,000 women.
Pairs of shoes, okay. What did that show?
Well, even without seeing the graph, the description is vivid. The range was huge, from 5 pairs up to 60.
Wow, 60 pairs.
Yeah, and specific counts, like 160 women had exactly 18 pairs. Only 20 had just 5. The median, the middle point, was around 19 pairs.
So half had 19 or fewer, half had more.
Right, and get this. 15% owned more than 30 pairs, and 5% had over 50.
See, just hearing those numbers gives you a real feel for the distribution, doesn't it? You instantly get a sense of where most women fall, the spread, the extremes.
It really does. It paints a picture quickly.
That's the power of a good visual.
Then there's example 1.6. This one's a bit of a puzzle. A histogram of exam scores, but the vertical axis isn't labeled.
Ah, so you don't know the exact number of students in each score range?
Nope. No counts.
But, and this is clever,
Yeah.
you can still figure out the relative frequencies
How?
by looking at the area of each bar relative to the total area of all the bars.
Yeah.
Think of the whole histogram area as a 100% of the students. Then the percentage of the total area that one bar takes up. That's the percentage of students in that score range.
I see. So in this example, the bar for scores 60-70 takes up 10% of the area.
Meaning 10% of students score between 60 and 70.
And 70-80 is 40% of the area, 80-90 is 30%, and 90-100 is 20%.
Exactly. It really drives home that key idea. In a histogram, relative area equals relative frequency.
That's powerful. Even without exact numbers, the shape and proportions tell the story. Okay, let's switch gears again. Stem plots, or stem and leaf displays. Sounds kind of organic.
It does, doesn't it? They're actually a really neat way to visualize quantitative data, especially if you want to see the individual values and the overall shape.
Individual values, too. How does that work?
Well, it's split by a vertical line. You have the stem on one side, usually the leading digit or digits of your data.
Okay.
And the leaf on the other side, typically the last digit.
We have an example here. Urinary BPA levels in kids, measured in NGML. Data ranges from 0.2 up to 5.2.
Right, so for a stem plot there, you might use the whole numbers, 0, 1, 2, 3, 4, 5, as the stems.
And the decimal part as the leaf. So like 0.2, 0.4, 0.7, 0.7 would be stem 0 and leaves 2, 4, 7, 7.
Exactly. You list the leaves in order next to their stems. So stem 0 would have leaves 2, 4, 7, 7, 8, 8, 9. Stem 1 would have 0, 0, 0, 3, 4, 4, 7, 9, and so on.
Ah, I see. So you can see the shape where the numbers bunch up, but you haven't lost the original measurements?
Precisely. You get both the distribution and the detail. And a crucial tip from the source, always include a key.
A key.
Yeah, something that clearly explains what the stem and leaf represent, like key 1.4 equals 1.4 NGML. Super important for clarity.
Got it. And there's a note here, too, about BPA levels over 2 NGML being linked to higher overweight risk. That adds context.
Definitely. Context is vital for interpretation.
We also have a push-up example. 9-stop push-ups by teens, ages 15-18, data from 2 up to 50.
Right. Same idea. A stem plot would show the spread of push-up ability, maybe using the 10 digit as the stem and the units digit as the leaf, while keeping each person's score visible.
Okay, so we've seen these different visual tools. Now, how do we actually describe what we're seeing in them?
Good question. It's not enough just to make the graph. You need to talk about it. Our source highlights 4 main things to look for and describe.
Core key aspects.
Yeah. Center, spread, shape, and any unusual features.
Center, spread, shape, unusual features.
Some people use acronyms to remember, like SOCS, shape, outliers, center, spread, or CUSS, center, unusual, shape, spread.
SOCS or CUSS.
The
Okay.
critical thing is to always describe these features in the context of the actual data. What does the center mean for these AP classes or these shoe pairs?
Right, related back. So let's start with center and spread. Center is like the middle.
Yeah, basically a typical value, a point that roughly splits the data in half, gives you an idea of where things are centered.
And spread.
Spread tells you about the variability, how scattered is the data. The simplest measure is often the range from a minimum value to the maximum value.
Like we saw with the AP classes, center around 2, spread 0 to 4.
Exactly. Or the shoes. Center about 19 pairs, spread 5 to 60. Big difference in spread there.
Yeah, definitely.
And the tip here is always describe center and spread together. They give a much more complete picture when paired.
Okay, center and spread together. What about those unusual features? You mentioned clusters and gaps.
Right. Clusters are like natural subgroups showing up in the data. The example given is teacher salaries in Ithaca, NY. Maybe you'd see distinct clumps for public school teachers, college profs, university profs.
Ah, different groups within the data.
Exactly. Gaps, on the other hand, are just holes, empty spots where you'd expect data, but there isn't any. Like maybe GPAs for students getting Dean's List. If the cutoff is really high, you might see a gap below that cutoff.
Makes sense. We also need to spot outliers.
Definitely. Outliers are those extreme values, way off from the rest of the data. Could be an error, could be real but unusual, worth investigating.
And modes, like unimodal, bimodal.
Yep. Modes are the main peaks or humps in the distribution. One peak is unimodal, 2 peaks is bimodal. You got to be careful not to call every little bump a mode, though. Look for the major ones.
We had that computer usage example, right? Bimodal.
Yeah, example 1.10, peaks mid-morning and mid-afternoon, probably work times, dip at lunch, and at one point in the evening, a potential outlier.
So as you see these features, and then you think about why they might be there.
Exactly. Ask questions about the context. Why the peaks? Why the outlier? That leads to understanding.
Okay, and the last big one was shape.
Right, the overall form of the distribution. There are some common shapes we look for.
Like symmetric.
Symmetric is one. If you fold it down the middle, the two halves are roughly mirror images. Think, ideally, about separate distributions for men's and women's weights. Each might be roughly symmetric.
Okay, what else?
Skewed. Skewed to the right means the long tail stretches out towards the higher values.
Yeah.
Like maybe ages of people living past 90 most cluster around 90, 95, but a few live much longer, creating a tail to the right.
And skewed left.
Opposite. The long tail goes down towards the lower values. Imagine scores on a really easy test. Most people get high scores, but a few might score low, pulling the tail to the left.
Got it. Right skewed, tail right, left skewed, tail left.
You got it. Then there's the classic bell-shaped curve. That's symmetric, but specifically with a central mound and tails sloping down smoothly. IQ scores are often cited as roughly bell-shaped.
Okay. Any others?
Uniform. That's when everything is roughly equally likely. The histogram looks kind of flat, horizontal, like rolling a fair die many times. Each number should come up about the same amount.
Right.
And remember, real-world data is rarely perfectly any of these shapes. We often say roughly symmetric or approximately bell-shaped. It's about the general pattern.
Okay, that covers the main descriptive elements. Now there was one more type of plot mentioned. Cumulative relative frequency plots, ogives.
Ah, yes, ogives.
Right.
Pronounced ogives. They sound a bit complex, but the idea is useful.
How so?
Instead of showing the percentage in each bin, like a histogram using relative frequency, an ogive shows the running total, the cumulative percentage up to a certain value.
Cumulative, so it always goes up or stays flat.
Exactly. It plots points representing the upper boundary of each class interval against the cumulative relative frequency. It starts at 0% and ends at 100%.
And what's that good for?
Really good for finding percentiles. Like you can easily look at the graph and find the value below which, say, 25% of the data falls, the first quartile, or 50% the median, or 75% the third quartile.
Okay, percentiles. We have an example, U.S. school enrollment by age in 2015.
Right. Looking at that ogive, what can you tell?
Well, it shows about 15% enrollment below age 5. The median, the 50% mark, hits around age 11. And it looks like 95% of enrollment is below age 30. You can also estimate the middle 50%, the inner quartile range. Looks like maybe between ages 6 or 7 and age 16.
See. Lots of info about position within the distribution comes right off the ogive.
And the shape of the ogive itself tells you something about skewness.
It does. Think about it. If data is skewed left, lots of high values, the ogive will rise slowly at first, then get steep towards the end.
Because you're accumulating the less frequent low values slowly.
Right. And if it's skewed right, lots of low values, it rises steeply at the beginning and then flattens out more gradually as you add the fewer high values in the tail.
Okay, steep, then slow for right skew, slow, then steep for left skew.
You've got it. Example 1.12 describes 3 teachers' grading styles. Abrams gives high scores, left skew. Connors gives low scores, right skew. Brown is more spread out, maybe symmetric. Their ogives would reflect those shapes.
Interesting how the plot shape connects back.
It all ties together.
Okay, so let's try and wrap this up. When we're looking at data visually, the main things to describe are...
Shape, center, and spread. Those are the big 3.
Right. But also keep an eye out for the unusual stuff.
Absolutely. Clusters, gaps, modes, outliers, and always talk about them in the context of what the data actually represents.
Don't just say it's skewed left. Say the exam scores are skewed left, meaning most students did well.
Perfect. And think about why you might be seeing those features. What could explain the clusters or the outliers?
And remember the different tools. Bar charts and maybe dot plots for categorical data.
And histograms, stem plots, ogives, sometimes dot plots again for quantitative data.
And that key histogram insight. Relative area equals relative frequency.
That's a really fundamental one.
It really circles back to that first idea, doesn't it? Drawing the picture helps you understand. It cuts through the complexity.
It gives you that immediate impression, spots patterns you'd miss just looking at a list of numbers.
So thinking about this, maybe consider the last bit of data, the last statistic or report you came across. How could visualizing it differently have changed what you took away from it?
That's a great question. What hidden stories might be sitting in the data around you, just waiting for the right picture to reveal them?
Food for thought. We'll definitely be exploring more ways to understand data in future deep dives.